Hi, folks. Today we are learning about periodic groups. And we're going to learn how to draw Lewis structures and talk about how atoms form charges. Let's just jump right in. One of the groups we are going to look at today include a gas called argon. Argon is known for being very stable and unreactive. And that's true for all of the elements in the group in which argon belongs. And argon is used to fill window panes for double paned windows. So these are newer windows that are more insulating. So you see them on newer houses, or if your windows get upgraded at home, then they'll usually be double paned. And you can tell that they have argon in them because they have a slightly green tint. And the reason why they fill windows with argon is because it is more dense than regular atmosphere. So it is a better insulator than just regular atmosphere. Also, because it has a green tint, you can tell when there's no more argon in between, and you can tell when it's not quite as insulating once the windows wear out a little bit over time. And one of the reasons also they use argon is because it is so unreactive and safe. So if any of the argon leaks out of windows, it's okay because it's not going to harm you. And we're going to learn about why that is today. To start, let's first draw a Bohr model of fluorine. You should have your periodic table with you and your note sheet, and take notes along with me while I do this. Fluorine is the 9th element on the periodic table. It has 9 protons, and it is going to have 10 neutrons after we take a look at after we subtract the number of protons from its atomic mass. But more importantly, because it has 9 protons, it's also going to have 9 electrons. So that's 2 on the first level and 7 on the second level, for a total of 9 electrons. And what we see here is, one of the things that we've learned about is that fluorine has 7 electrons on the outer shell. These are called valence electrons. That's these electrons right here. It has 7 valence electrons. And these valence electrons tell us the most about how fluorine is going to behave and react. One of the ways that we can show valence electrons are through what's known as Lewis structures. Lewis structure, well, this guy named Lewis came up with a way to draw and represent atoms, elements, and compounds. And the way it works is we have the letter for fluorine, the atomic symbol for fluorine, and on the outside, we just draw its valence electrons. So fluorine has 7 valence electrons. So that's 1, 2, 3, 4, 5, 6, 7. So I draw 7 dots around fluorine, and that's the Lewis structure for fluorine. Let's do oxygen. If you see here, oxygen is the 8th element. And if we look at the periodic table, and if you look at your periodic table, you might see the little numbers in the top right-hand corner of oxygen's box. Or you might also just count, and you'll see that oxygen has 2 on the first level and 6 on the second level. And it has 6 valence electrons. So I'm going to draw 6 dots around oxygen. That's oxygen with 6 valence electrons. Let's now do neon. Neon is the 10th element, and it's going to have 2 on the first level and 8 electrons on the second level for a full outer shell on the second level. So it's going to have 1, 2, 3, 4, 5, 6, 7, 8. Because we spent time practicing electron configurations, you should basically going through the Bohr model should be relatively easy for you now. And all you need to know is that what we are drawing here are electrons on the outer shell. Let's now do sodium. If we were to draw the Bohr diagram for sodium, how many electrons would it have on its outer shell? It would have 2 on the first level, 8 on the second level, and 1 on the third level. So I'm just going to draw sodium with 1 electron. What about lithium? If you drew the Bohr diagram for lithium, or if you look on the periodic table, you would see that lithium has 2 on the first level and also just 1 on its outer shell. So these are Lewis structures, and it's basically drawing the number of valence electrons around each symbol. Now, I want you to notice a couple of things. The first thing I want to tell you about is the Octet Rule, and we're going to fill that in down here. The Octet Rule is where atoms tend to gain or lose. So I'm going to put gain/lose. They either gain or lose electrons to form a full, I'm going to write it up here, full outer shell. Nope. Accidentally zoomed in there. Need to get my pen back. A full outer shell. And this is usually 8 electrons. What do I mean by this? Well, if you take a look at fluorine, fluorine only has 7 electrons on its outer shell. And what the Octet Rule tells us is it would prefer to have a full outer shell, which is usually 8. It tends to gain an electron. It will add an electron from somewhere. And when it gains an electron, it forms a minus charge because electrons are negatively charged. So if I gain an extra negative electron, I will now have a negative charge. When it does that, it forms what is called an ion, which is our second definition. An ion is an atom which has gained or lost electrons. It has charge. It has a charge. So I can either gain or lose an electron, and when I do that, I have a charge. Let's do oxygen, for example. Oxygen currently has 6 electrons on its outer shell. What it wants to do is gain 2, which I'll circle to show that those have been gained. When it does that, it forms a charge and it forms an ion. And because it's gained 2 negative electrons, its charge is now -2. What about neon? Neon has 8 electrons on its outer shell. And that's exactly where it wants to be. How many electrons do you think it will gain or lose? Well, because it has 8 already, it won't gain or lose any electrons. It'll stay just as it is, and it will not form an ion, and it will not form a charge. We could put a charge of 0 there, but we usually don't do that. we usually just write a symbol of plus or minus if it has gained a charge. What about sodium? What is sodium going to do? Well, sodium only has one electron on its outer shell. In fact, let me go ahead and draw the Bohr diagram for sodium. Sodium has 11 protons and 11 electrons, and it has 12 neutrons. I'm going to put 11 electrons here, 2 on the first level, 8 on the second level, and 1 on the third level for a total of 11. Well, rather than gain 7 electrons, it could gain 7. That is, in theory, possible. But that would give it a charge of -7. And that would be a very high amount of charge. That is not usual and not stable. That's too much charge to one side. So rather than gaining 7 electrons, what it likes to do is actually lose an electron. It likes to give, and by the way, this is sodium. It likes to give this electron away. And when it does that, look at how it has a full outer shell. 8 electrons satisfying the octet rule. The charge that it will form when it loses 1 electron is +1 or plus. They mean the same thing. So what it likes to form, if I were to draw the Lewis structure of sodium, it likes to form sodium plus, where it loses that 1 electron. What do you think will happen to lithium? Lithium has only 3 electrons. 2 on the first level and 1 on the second level. It does the same thing. It loses this 1 electron, forms a plus charge. This is now lithium plus, and it has a full outer shell. Even though it's not 8, it does have a full shell on the outside, so it is stable. Lithium likes to lose an electron and form lithium plus. In summary, all of these elements will gain or lose electrons in order to form a full outer shell, which is usually 8 electrons. And when I gain electrons, I develop a negative charge, which was the situation here. When I lose electrons, I develop a positive charge. There are a couple of other ways to express this, why we have charge. For example, fluorine negative. Well, fluorine negative has 9 protons, but at this point, it has 10 electrons because it has gained 1. It will have 2 on the first level and 8 on the second level. And now we see we have 1 extra electron. That's why I have a charge of -1. Here, oxygen has 8 protons, and it too has 10 electrons. It has gained 2 electrons, so it has a charge of -2. Here, neon has 10 protons, 10 electrons, so its charge is 0. Sodium here has 11 protons and only 10 electrons, so it has 1 proton extra. That's why it has a positive charge. And lithium, in the same way, has 3 protons, 2 electrons, so it has 1 proton left over, which is positive. So you need to be able to figure out what charge something has either by comparing its protons and electrons, or by looking at the symbol, or by seeing whether or not it's going to lose or gain electrons to form a full outer shell. Don't worry, we're going to continue to practice this. The way elements behave to either gain or lose electrons and to form ions can be seen in how the periodic table is structured. And we are about to learn how the periodic table is structured into certain groups to show that. First, I want to define a couple of key terms. A row on the periodic table is called a period. A column is called a group. Let's take a look at why this is. Let's take a look at the periodic table, and you can label in your periodic table and follow along with me. The first thing we're going to label are charges that these elements tend to form. Notice how lithium and sodium are on top of each other. Both of these, as I showed before, tend to form a charge of +1. You should write a +1 on the top of this group in the periodic table in your notes and also on the periodic table that you have on your pink sheet. For beryllium and magnesium and calcium, everything in this group tends to form a charge of +2. And I'll label it right here at the top, +2. They have 2 electrons on their outer shells. They tend to lose those 2 electrons to form a +2 charge. These groups right in the middle, right here, all of these form variable charge. We don't really know exactly, we can't predict right off the bat from the periodic table which charge they will form. We can eventually develop rules to predict them, but we cannot currently do that with the information that we have. Here, this group right here tends to form a charge of -3. They tend to gain 1, 2, 3 electrons in order to form a full outer shell to get them to the end of their row. Oxygen, sulfur, selenium, tellurium, and polonium, this group tends to form a charge of -2. Fluorine, chlorine, bromine, and iodine, these tend to form a charge of -1. They tend to gain an electron to form 8. That's what we saw earlier. And this group right here tends to have a charge of 0. What we just wrote are the charges that these groups tend to form. And notice that it goes in a regular repeating pattern across the way. And it has to do with the fact that the number of valence electrons increase as we go from left to right across the periodic table. Lithium has 1 valence electron. Beryllium has 2 valence electrons. Boron has 3 valence electrons. Carbon has 4, nitrogen has 5, oxygen has 6, fluorine has 7, and neon has 8 valence electrons. And you see this pattern regularly repeat from left to right across every row on the periodic table. That's why it's called a period. A period is something that regularly repeats. That's why they call magazines periodicals. That's why I might say I might periodically check in. I'm going to regularly do it. And so these patterns that go from left to right across rows is why rows are called periods. And because every element in each column tends to form these charges, they tend to share certain properties, which is why we call them groups. And each group has its own name, which we are going to label now. This color right here, your printout may be in black and white, so you may not see the colors exactly. So this color right here, this is the alkali metals. They are very reactive. and you should write this here. Group 2 is also very reactive. Group 2 is called the alkaline earth metals. Oops. Group 2 is called the alkaline earth metals, and they are also very reactive. That's this group right here. This color you can't quite see on your black and white chart, but it refers to this whole group, and these are called transition metals. Transition metals aren't so reactive. Some of them, like gold, are not reactive at all. This blue group right here, which refers to this underneath the staircase, this blue group, these are called the poor metals. They're poor metals not because they didn't get Christmas gifts for Christmas, like was the case for me when I was a very young child. I didn't get Christmas gifts for a few years because we were poor. That's not why they're called poor metals. They're called poor metals because they don't act like metals very well. They don't conduct very easily. They're not very malleable. They are not very metal-like. That's why they're called poor metals. You wouldn't want to use them to conduct electricity or do any of the other things that you usually do with metals. This whole group right here, and actually it includes the noble gases to the left of the staircase, are nonmetals. Everything to the left of this staircase, which I'm going to highlight here, are called nonmetals. This is the staircase. Everything to the right are called nonmetals. Everything to the left of the staircase are metals. Everything to the right are nonmetals. This last group that tends to form a charge of 0 and it doesn't react, these are called noble gases. And I'm going to make a note right here, which you should write on your sheet, is that they are non-reactive. That's why they're called noble, because it's hard to get them to react to things. It's like when somebody is really getting on your nerves. If you want to be noble, just don't react. This is non-reactive. There's one other group that's not captured by these colors that I want to emphasize here. This group right here, they're called the halogens, and halogens are very reactive. All right, so I've covered the main points, which is you should have your charges written on your pink sheet. You can even have the group names. And the charges, again, the first column is +1, second column +2, -3, -2, -1, 0. These are the charges that each group tends to form. We went over the names of each group, from the alkali metals to the alkali earth metals, which is group 2, to the transition metals, which is in the middle, to the poor metals. Everything to the left of the staircase are metals, and everything to the right are nonmetals. And we further defined the nonmetals for this group right here, which are called the halogens, and the very end group, which are called the noble gases. Alkali metals, alkaline earth metals, and halogens are very reactive because it's easy for them to gain or lose electrons. Noble gases are non-reactive. They have a full shell, don't want to react, and so they are non-reactive. Let's quickly go through the differences between metals and non-metals, and that will conclude our lesson today. Here are the differences between metals and non-metals. On the left-hand side are metals. Metals are malleable. That means they are able to be formed into sheets. You can remember that because malleable sounds like mallet, which means which is a type of hammer, and you can hammer metal into sheets. Ductile means metal is able to be pulled into wire. You're able to pull it into wire. What is a word for shiny? That's luster. Metals have luster, and it means they are shiny. And they are conductive, which means they are able to conduct electricity. Non-metals, on the other hand, if they're solid, they're hard and brittle. They're not malleable. They'll snap and break easily if you put pressure on them. Others tend to be gases. A lot of the non-metals are gases, and none of them in general are conductive. Today, we started out by reviewing Bohr diagrams and seeing how atoms like to gain or lose electrons to form a full outer shell. It also gives them a charge. They are called ions when we do that. And their charge can be seen by the number of electrons they gain or lose, by what's written on their symbol, or by comparing the number of protons and electrons after they have gained or lost electrons. Those are ions. Then we talked about how rows are periods because there's a regular repeating pattern of valence electrons across the periods, and it regularly repeats. We talked about how each column is called a group because they share certain features like a common charge. And we talked about the group names and how reactive or unreactive are, and whether or not they are to the left of the staircase, meaning metals and non-metals, and concluded with qualities of both metals and non-metals. That's it.